Okay, so as we already know then, CRP, the modified CRP that was used in this experiment contains a single cysteine residue which maps to the activation region. Okay. And so now what we want to do is to try to transfer this label to RNA polymerase, and in that way prove that when CRP and RNA polymerase are bound to the promoter, that activation region 1 is in direct contact with some portion of RNA polymerase. One thing that's left out of this scheme here is that these two proteins are both bound to the LAC promoter. Okay. So CRP is bound to the CRP site in the LAC promoter, and RNA polymerase is bound to the promoter itself. And so then what you do is you irradiate with UV light. Okay. And when you irradiate with UV light, basically that causes a reaction to occur in this azido group up here. Okay. And so here we see the azido group. Okay, here's a resonance structure of the azido group. When you irradiate with UV, that results in the cleavage of this bond here. You release diatomic nitrogen, and then you leave behind then this so-called nitrene derivative of nitrogen, this nitrene form of nitrogen. Okay? And this nitrene form of nitrogen is not happy. Why not? How many valence electrons does it have? 1, 2, 3, 4, 5, 6, right? So you count the covalent bonds as 2, and then each of the electrons in the lone pairs counts as 1. So 1, 2, 3, 4, 5, 6. So this does not have an octet of electrons in its valence shell. It's therefore extremely reactive. Okay, and so it's going to grab electrons wherever it can find them. Okay, and so if it's bound in close proximity to RNA polymerase, it will attack the RNA polymerase, some atom X on the RNA polymerase, and form a covalent bond to therefore complete its valence shell, its octet of electrons in the valence shell. Okay. And so now at this point we've cross-linked the CRP to the RNA polymerase. We haven't transferred the label yet. In order to transfer the label, we need to break the linkage between CRP and the labeled residue. And so how do we do that? We need to break this disulfide bond. And you should all actually know how to break disulfide bonds because it was an important step in one of the experiments that you read about for discussion this week. You can just treat with this reducing agent called DTT. You'll cleave this disulfide bond. And now you've transferred the label from CRP to RNA polymerase. So a scientist named Richard Ebright carried out this experiment. The reference is given a few slides earlier. And then he looked to see whether he had indeed transferred the label to RNA polymerase. Okay, and so here is sort of a schematic, simplified view of the result he got. So what he did was he took the RNA polymerase. After he carried out this series of reactions, he ran it out on a SDS polyacrylamide gel to separate the subunits, and then he stained that SDS polyacrylamide gel with a protein stain, something called Kumasi blue. If you've taken 153L, you've done this exact kind of thing. And so we see then the various subunits of RNA polymerase. We see all this when we stain with Kumasi blue. We see all the subunits of RNA polymerase: beta prime, beta, sigma, alpha. I didn't draw in omega. We can imagine that omega ran off the bottom of the gel because it's so small. Okay. And then what you can do is to see which of these bands has become radiolabeled by just taking this gel then and putting it in the dark against a piece of X-ray film, and then after a suitable exposure period, taking that X-ray film and developing it. The X-ray film will then give you a black band wherever it was next to a radiolabeled protein. Okay, and what they saw was that the label did transfer to RNA polymerase, and in particular, it transferred to the alpha subunit. Okay. So further experiments showed that the label, I don't know why that's not working. The label didn't just go to any old part of the alpha subunit. It went to the C-terminal domain of the alpha subunit. So the alpha subunit actually contains two domains, two globular domains. Okay. We can imagine that it looks something like this, right? It contains an N-terminal domain and a C-terminal domain. And they're connected by a flexible linker. And when we looked at the structure of RNA polymerase, the X-ray crystal structure of RNA polymerase, actually we didn't see the C-terminal domain. Because this linker is so flexible, there was a lot of mobility, and therefore this C-terminal domain was blurred out. So the only thing we can see in the X-ray crystal structure of the RNA polymerase core, the RNA polymerase holoenzyme, is the N-terminal domain. This is the part of the protein that binds to the beta and beta prime subunits and holds them together so that they can come together and form the active site. This protein, as we'll see, actually, this part of the protein actually plays a regulatory role. Okay. And by treating with a chemical reagent which actually cleaved the two halves of the alpha subunit apart from one another, they could show that the radial label was associated with the C-terminal domain. Okay. So the conclusion is that AR1 is in close contact with the alpha subunit C-terminal domain.